So it's a great pleasure to have Professor Chandan Dalawat with us. He's a professor in HRI. He was a former colleague of mine. He's a number theorist, and as you will see, he makes concepts really clear to the audience. As I can see, there are many physics students here who are very interested in maths, so we'll have some fun.
Thank you very much for the introduction. First of all, I'd like to thank this institute and Rukmini in particular for the opportunity to visit this place. It's a place which is difficult to believe exists if you don't actually see it. So, I'll make my talk really accessible to everybody. So if you have any questions, please interrupt and ask for clarifications. You know, usually when we, as mathematicians or physicists, do our work, we do some very technical kind of things, and they are often not easy to communicate to a broader audience. Sometimes, as is going to be the case today, you come across things which are really somewhat elementary, and I'll be happy to discuss these things here. So my talk will consist of 3 parts. So this will be what went before Galois, and then there are 2 memoirs of Galois which I will discuss, and finally I will talk about some footnotes. So that's a plan, and this is about algebraic equations, polynomial equations. So one of the most basic things in mathematics. So for example, the earliest thing that you can think of are these quadratic equations, right? Ax squared plus bx plus c equals 0. And for it to be quadratic, this a has to be different from c. And we all know how to solve this, right? So the solution is given by something which you remember from school. So there are a few things to remark about this solution. So the first thing is that 2 has to be different from 0 if it has to make sense. So which is to say that this is valid in any field of characteristic different root. So if you don't know what a field is, don't worry. It's just a system of entities which may be called numbers, which can be added, multiplied, and in which division by non-zero entities can be performed. So this is an abstraction of the usual system of, let's say, rational numbers, real numbers, complex numbers. They are all fields. Another thing to notice is that this generality A, B, C is kind of spurious. You can always assume A equals 1 because you can divide by A if A is different from 0. So there is this formula for solving quadratic equations. So the next thing would be cubic equations. So there are x cubed plus ax squared plus bx plus c plus c. Now, I don't know how many people are familiar with a formula for solving cubic equations like this. But in the 16th century, Italy, so there are people like the most famous among the people who contributed to a solution of this cubic equation is somebody called Cardano. There were also people called Del Ferro, etc. And what they did was to give a formula. This is a formula for solving such things. For x in terms of the coefficients, so the coefficients here are a, b, c, and involving only the four arithmetic operations plus, minus, times, division, and just as you have square roots here, for solving the cubic, you will need not only square roots, but also cube roots. So what I want to say here is that there is a formula similar to this quadratic formula for solving the cubic in terms of the coefficients, and the only operations you perform on the coefficients to get a solution are the four arithmetic operations and the extraction of square roots and cube roots. There is no point, I can write down the formula or you can look it up. There is no point in telling you what it is. I just want to say that there is such a thing. Similarly, for quadratic equations, Quartics, the same thing holds for quartics. Quartics are equations of degree 4, and there was a student of Cardano by the name of Ferraro, I think, who gave a formula, and that's not very difficult once you know how to solve the cubic, who gave a formula for the roots of a quadratic equation involving only the coefficients, the four arithmetic operations, and the extraction of roots. Okay, so this is called solvability by radicals. So solvable by radicals. These are radicals.
So the radicals in the Quartic case, it is just fourth root, or does it go to some higher roots?
No, it doesn't go higher than fourth. No. Yes.
In what sense arithmetic operation and radicals are equivalent?
They are not equivalent in any sense. I mean, you want to express some number in terms of some other numbers. What are the functions involved in expressing this? Like here, you just have to use plus, minus, division, multiplication, and extraction of square roots. So the question is, what operations do you need to perform on the coefficients in order to get a root? Here, what is being said is that the only operation you need to perform, it's enough to perform the four arithmetic operations and this extraction of roots.
Found these radical nth root, finding nth root. In the past, people will found that easier to. It's not easy to find nth root at the number in the past.
That's a different question altogether. Yes.
So these roots are in some sense we're using the exponentiation function.
No, you're not using exponentiation anywhere.
Something to the power of.
Okay,
So in that sense, we are utilizing the coefficients present in the expression of the LHS, and we are using also another function.
Yes.
That is present in our Theorem analysis. So, in what sense are we? If you were to look at other equations, say higher order equations,
yes.
One might think that there may be other functions which might be brought into our
So I'm coming to higher degrees. So I've just done degree 2, 3, and 4, and 5 is next. So let's come to Quintics. Quintics, see, Lagrange looked at the method of solution of these Quintics and Quartics and came to the conclusion that this method is unlikely to work for Quintics for equations of degree 5. And show that it doesn't work and that there is no other method for expressing the roots of a quintic in terms of the coefficients using only these operations. But Abel was the first one, and Buffini Theorem had written an entire book trying to show that there are quintic equations which cannot be solved in terms of radicals. So as you were saying, maybe there are other functions which are required, and that's what they proved. So Abel proved that there are quintics. There are quintics whose roots cannot be expressed as in terms of radicals. So if you want to express them in terms of the coefficients, the operations you will need are more than just the usual arithmetic operations and extraction of roots. You'll need something more. That's what Abel proved. Okay. So we'll stop at this degree 5 quintics, and I have, yes.
So, what kind of techniques did you use?
So you asked me difficult questions. So there's a paper by, so you see, the techniques today, what we will use today, I'll explain just now. So at that time, what Abel used must have been something ad hoc. This was systematized by Galois, and this is what I'm going to say now. Explain how, right? So what Galois did, and this is fundamental, absolutely. He was some 18 or 19 years old when he did this, and it's absolutely revolutionary. Okay, so what he did was, he said we have been looking at equations of degree 5, let's say, and we have found some which are not solvable. That doesn't mean that no equation of degree 5 can be solved using radicals. Some can be, some cannot. And his question was, which are the ones which can be solved by radicals and which are the ones which cannot be solved by radicals? How do you say? How do you tell them apart? It's partly answering your question. Okay? So, and that's what Galois worked on, and he came up with a very nice theory which today is called Galois theory. And let me briefly explain what that theory is. So he says, you start with an irreducible equation, let's say f. So f is some equation of the kind x to the n plus a n minus 1, x to the n minus 1, plus b n, not b, a n minus 2, x to the n minus 2, etc. up to k n equal to 0. And this polynomial is supposed to be irreducible. Because if it can be written as a product of two factors, then the roots are going to be the roots of the factors which are of smaller degree. So, if you want to, I mean, it's enough to construct irreducible equations. So he said, you start with an irreducible equation, and what we know is that it's going to have some roots, some n roots, x1 to xn. We are just calling them x1 to xn. That's not saying that we have found what those roots are. We are just saying that there are n roots. An equation of degree has n degree n has n roots. Let's call them x1 to xn. And so they can be permuted in various ways. So if you have n objects, you can permute them in various ways, n factorial ways to be more precise, right? And you get a group. That's one of the most basic examples of a group in fact, one of the earliest instances of a group is you take some n objects and you permute them in all possible ways. They form a group. And that group is a finite group of order n factorial. Okay? So that you can do with any n objects. Those n objects don't have to be the roots of some equation. But when they are the roots of an equation, then those n objects are actually numbers and they have algebraic relations among themselves. They may have some algebraic relations. What algebraic relations these n objects have will depend upon what equation you have taken. Okay? So now you look at only those permutations which preserve these algebraic relations. Okay? And they will form a subgroup. So what Galois did was to assign a certain subgroup. This, by the way, is S, German S. S for symmetric, it's called the symmetric group. Sn, n for n objects. And Gal F is the subgroup of this symmetric group, consisting of all those permutations of these n groups, which preserve all algebraic relations between these groups. So, for example, one of them could be the square of let's say x1 could be the square of x2. In that case, the permutation will have to send x1 to something which is the square of the thing to which x2 is set. That's called preserving algebraic relations. So he attached to an equation a group, a finite group.
Do you assume x1 till xn are all distinct?
Yeah, that's right. If the equation is irreducible,
Irreducible, of course.
they are going to be distinct.
Yeah.
Yeah. So that's the first thing. The second thing that Galois did was, so we just report here, F. So this is an equation and this is a group. The second thing is, he defined the solvability of a group. So he said, if you are given a group, I'll call some groups solvable. And which ones is he going to call solvable? So this is not the standard definition what I'm going to give you now. It explains what the concept is, gives you the idea. So the idea is that you just declare all commutative groups to be solvable. I have to tell you which groups are solvable. I am saying if your group is commutative, call it solvable. Then next, if G, if your group, this group that you're looking at, has a subgroup H, which is normal inside G, such that, so if there's a normal subgroup such that both H and G mod H are solvable, then G is solvable. We just declare it to be solvable if it is a smaller subgroup which is solvable and modulo which the quotient is also solvable. This is called the quotient. This is the smallest subgroup. If they both happen to be solvable, you call G to be solvable. That's it. This is sort of inductive definition of solvability. And he proved this big theorem, which is the crux of Galois theory. I mean, okay. Should be done in courses in Galois theory these days. Which is that an equation is solvable by radicals in this sense, which I'm erasing. So the third thing that Dalawat did was this theorem. Say that an equation f equal to 0, an irreducible equation, algebraic equation, is solvable by radicals if and only if the group which Galois attaches to it, called the Galois group of F these days, is solvable in this sense. Okay, so he has transferred the problem. The problem was to find out which equations are solvable and which ones are not. And the solution is to attach a group to this equation, define the notion of solvability for groups, and prove that your equation is solvable if and only if that group is solvable. Now, all this is fine.
This is not only for Quintic.
No, this is for general equations, arbitrary degree. So, for example, you see, let's take degree 3 for example. Then this group, this Galois group of F is going to be a subgroup of S3. In general, if you have degree n, then the Galois group is a subgroup of Sn. So, and this group is solvable. Why? Because S3 contains this group called A3, which is the alternating group, and S3 modulo A3 is sort of Z mod 2Z. So this group, which is not commutative, has a subgroup which is commutative because it's of order 3. It's commutative, therefore it's solvable. Every commutative group is solvable. And the quotient is also commutative, so it's solvable. Now S3 has a subgroup which is solvable, and modulo the quotient is also solvable, so S3 is solvable. So this one particular case of this theorem is that equations of degree 3 are solvable, which we knew. So it just confirms that you can re-derive the solvability of Quintics from this. But it tells you which equations of arbitrary degree are solvable and which ones are not. But such a thing is really useful only when, so you have transferred the problem from equations to groups. So you have to be now able to say which groups are solvable. Ultimately, you will have to solve the problem. I mean, you reduce one problem to another problem, but that other problem you have to be able to solve. So that's a fourth ingredient in his first memoir. So I'm talking about two memoirs of Dalawat. This is the first one I'm discussing. So that's the third thing in the first memoir. And the fourth thing is a criterion for certain groups to be solvable. And what is that? So this is for equations of prime degree. And the degree is a prime t. So this is the fourth thing, criterion solvability of groups, of certain groups, when the degree is a prime P. So he says, so your group is a subgroup of SP, P is this prime, SP is the symmetric group, and you have a subgroup of this symmetric group. He says it's going to be solvable if and only if it contains a subgroup of order P, of order little p. That subgroup is called capital P and its order is little p. So if it contains a subgroup capital P of order little p is given to you. That's the degree of your equation. And is contained in what is called the normalizer of P in S. So, which is to say, the picture is going to be your G inside ST is given. So, for it to be solvable, it should contain, okay, I should make precise the fact that this group is supposed to be transitive. This corresponds to the equation being irreducible. Okay. So you are given a transitive subgroup of SP and you are asking when is it solvable? And Galois gives a criterion. It says that it's going to be solvable if and only if it contains a subgroup capital P of order little p and is contained in the normalizer of this P inside SP. So G should contain P and it should contain the normalizer N of this P inside that SP. So this is something which is easy to verify. Okay. Don't worry about what the precise statement is. You can look it up in many places. The point I'm trying to make is that for transitive groups of prime degree, he gives a criterion for solvability. So the summary is that Galois associates to every polynomial equation a group. The important thing is that group is computable from the equation. He proves that the equation is solvable by radicals if and only if this group is solvable in his sense. And finally, he gives a criterion for groups of prime degree to be solvable. So that's a very explicit theory. Okay. That's his first memoir.
Sorry, but the explicit characterization of G from a given equation, is there a, what is the algorithm way to get G from a given equation?
Yeah, so actually what you do is, so let's say you have an equation with rational coefficients, and you reduce it mod to various primes. Okay, so you get an equation over a finite field, and you see what is the factorization of this over these finite fields. And so somehow by looking at what it gives you mod to various primes, you get information about elements of the Galois group. And once you have enough elements, you can say what is the subgroup generated by these elements.
Did Galois know that, or is that
Galois computed it from any place. I mean, he might not have known the entire algorithm, but today this can be done by computer algebra systems, for example. Given an equation to compute its Galois group is now it's routinely done by systems called Pari or Sage or things like this. Yeah.
Just have a doubt about the theorem. You said once you take the Galois group corresponding to the equation M,
Yes.
you asked whether that's solvable or not.
Yes.
But the example that you gave, you said so you were looking at subgroups of S3.
Yes.
Right. So S3 is solvable.
Yes.
But does that mean that the Galois group corresponding to F is solvable?
So if your F is of degree 3, then its Galois group is going to be a C. So
I guess all the subgroups of a solvable group are solvable.
Okay.
Right. Whereas S5 is not solvable. And that's the first place where you have some subgroups which are solvable and others which are not. That's why Abel could come up with an equation of degree 5 which was not solvable. So I don't know who asked as to how you go about proving that some specific equation cannot be solved by radicals. The answer is you compute its Galois group and see whether it's a solvable group or not. So if you have an equation of degree 5, some of them are going to be solvable and others not. For example, this criterion here, 5 happens to be a prime. So this criterion will apply. So if the degree of f is 5 and it's going to be solvable, if it's solvable, then the order 5 divides the order of the Galois group and the quotient, the order of the Galois group by 5. This divides 4. In particular, if an equation of degree 5 is solvable, then the order of the Galois group of F is either 5 or 10 or 20. That's it. These are the only possibilities. That's what I want. Whereas this S5, the order of S5 is, I don't know, 120 or something, right? So that's a big group. But the Galois group has to be a small subgroup if your equation is smaller by radicals.
So you wrote 5 there, but here it's, you have 10 in the list.
Yes. So
you said order of Galois group divided by 5 is divisible by 4.
Divides 4. So it has to be either 1, 2 or 4.
Divides.
Divides. So in
It's
general,
not divisible, but it's divides.
So in general, instead of 5, you can have P. Then P will divide the order of this Galois group, and this will divide P minus 1.
So that follows sort of
From this criterion. That follows from this criterion. Okay. So this is okay. This completes the first memoir. I don't know how much time I have.
It started a little late. So.
Okay, I have some time. Now I come to Galois' second memoir, and I'll use slightly modern terminology now. So these days we don't talk of explicit equations, no? If you have an equation, I mean, it first of all has coefficients in some field. So in some field, and your polynomial f has coefficients in that field. If it's an irreducible equation, then you can adjoin a root alpha of this equation to k to get what is called k of alpha. So this k of alpha, it's a bigger field, it's a field containing k and a root of this equation, and it's the smallest possible field in these properties. So that's called adjoining the root of this equation to k, so you get a bigger field. So you get what is called an extension of k. An extension is just a slightly bigger field containing your given field. Okay? And you can consider that bigger field as a vector space over the smaller field. Just as the complex numbers, for example, are a two-dimensional vector space over the real numbers. Similarly, if you have a field and if you have a bigger field containing this, then you can think of this in particular as a vector space over this field. And as such, it will have some dimension. If that dimension happens to be finite, then you say that the extension is a finite extension. So instead of polynomial equations, now you consider finite extensions. That's the modern sort of way of looking at things. One of the reasons for doing it is that an equation has to be chosen. This is more sort of invariant language. You don't have to make any choices. Just as, you know, there's a difference between a vector space over R of dimension 3 and R3. They are isomorphic as objects, as vector spaces. But the difference is that here you have a canonical basis, whereas in general a vector space doesn't come with a basis. So similarly, what we are looking at here is a field and some finite extension of that field. Now, here's what Galois defined. So he said, okay, even before I define this, let me come back to this. So, yes.
Finite extension means it's a finite dimensional vector space.
Exactly. It's a field.
No, L is a finite dimensional vector space. And it is finite extension.
That's right. No, it's right. So, we start with the field K and a bigger field L containing K. So that's called an extension. It's going to be called a finite extension if, when you consider L as a vector space over K, its dimension is finite. Okay, so for example, R is an extension of Q, but that's not finite. It's not a finite extension. Because the dimension of R as a vector space over Q is finite. Whereas if I take Q and adjoin minus root of -1, that's a finite extension because the dimension of this as a vector space over this is 2. That's a finite extension. So you take any field, any finite extension, and then you have another extension called L hat, which is called the Galois closure of L. So what is this? So, okay, you do not have a Galois closure for an arbitrary finite extension. There is a technical condition called separability, which I'm not going into. If it is separable, then it has something called a Galois closure. And the Galois group L hat over K is what Galois attached to this extension. Okay. So given a finite separable extension, you have a Galois closure Let me explain in terms of these polynomials what this corresponds to and what that corresponds to. You have a field k, you start with a polynomial f with coefficients in k, and there I explained how to adjoin a root of that polynomial to get an extension. So you can adjoin, L can be obtained by adjoining a root of some polynomial to k. But adjoining one root is not the same as adjoining all the roots. So L hat corresponds to adjoining all the roots of your polynomial to k. So the simplest example would be you take q, you take the polynomial, let's say x cubed minus 2, then of course this L is going to be q to which we have adjoined a cube root of 2. That's an extension, but it's not what is called a Galois extension. This field doesn't contain the other two roots of this polynomial. This polynomial has 3 roots. I've adjoined only one of them. And L hat is going to correspond to this. If you adjoin a cube root of unity and a cube root of 2, then you have all the 3 roots of this polynomial in this. So that's what the Dalawat closure is, and this is a finite extension of G.
But is it quite possible that the Galois closure and the finite extension L?
You are absolutely right. Yes. In particular, yeah, that happens very often. That happens.
So does this mean just by attaching one you get the whole list?
Yes, that happens.
So x to the instead of x cubed minus 1 if you had.
For example, that's right. X cubed minus 1 is not irreducible, but there are.
Okay, yeah.
But for example, no, the principle is right. Principle is correct. So if you take, for example, x to the p minus 1 divided by x minus 1, then you get this polynomial x to the p minus 1, x to the p minus 2 plus x plus 1. It so happens that this polynomial is irreducible, and if you adjoin a root of this, root of, let's call this polynomial f sub p, or the standard notation is phi sub p. It's called a cyclotomic polynomial. So if you adjoin a root of this polynomial, then it so happens that it contains all the other roots. Actually, it's easy to see why it contains all the other roots, because the other roots are, if alpha is one of the roots, then the other roots are alpha squared, alpha cubed, up to alpha, I don't know, p minus 1 or p minus 2, or alpha to p minus 1 is 1. Right, it's alpha to p minus 1, correct? That makes, yeah. Yeah, that's it. So that happens often.
In this case, any root if you attach it will extend, right? This particular. Because all roots seem equal.
No,
Here's an important point.
because p minus 1 is even, so
No.
if you adjoin alpha square, you wouldn't get you wouldn't get the whole.
No, you'll get the whole. No, because alpha can be written as a power of alpha square. You see, what happens is, you think of it in terms of this. So here is zeta, or call it alpha square. But this alpha is also a power of this alpha square. They generate the same sort of circle. But his point was, which root are you adjoining? Are you adjoining alpha or are you adjoining beta? But the point is that if you take an irreducible polynomial and its real roots are alpha 1, alpha n, if n is the degree of this polynomial, then you get sort of you might think that you get many different extensions. You get Q alpha 1, Q alpha 2, and these are two kind of extensions of Q. Now, it may happen that they are different. So if you are thinking of them as subfields of complex numbers, for example. So if you are thinking of Q root of 2 and Q root of 2 times Q root of 1. Now, I don't know what the standard English notation, sub omega is perhaps the notation in some textbooks. But so these are different subfields of C, but they are isomorphic as extensions of Q. So we are only looking at things up to isomorphism here. If you adjoin two different roots of an irreducible equation, the extensions you get are going to be isomorphic. So it doesn't matter which root you are adjoining. And in fact, in general, doesn't even mean because you can't distinguish roots of a polynomial. It's an irreducible polynomial. There's no way of saying this root. I mean, there are different roots, of course, but there's no way of saying that particular root and that, but there's no way to distinguish roots of a polynomial. Anyway, so if you adjoin different roots, you get isomorphic extensions. So because I wanted to define primitivity. Yes. So before I want to define primitivity, are there any questions? Okay.
What if there are a lot of there will be some algebraic relations between the roots, right?
Yes.
So then can you say something about the extensions? Like, I mean, symmetric polynomials are there.
Right.
But other than that, if there are many other, I don't know what I
The symmetric polynomials allow you to express the coefficients
in
of
terms
your
of,
polynomial
that's right.
in terms of the roots.
Yeah.
But that's in general. I mean, there's no. That works for any polynomial.
But that's not considered a algebraic relation. What exactly do you mean by algebraic relation? Supposing some of the roots is
You are right. Okay, so you are right. So that will count as an algebraic relation. For example, if I take an equation of the kind take such an equation, if it's irreducible and the roots are alpha 1 up to alpha n, then the sum of these roots, okay, let me put a minus here so that alpha 1, alpha 2, alpha n is going to be equal to this a n minus 1. You are right, this is an algebraic relation between the roots. But that's going to be preserved by every polynomial, every permutation. But the permutation is going to take this to itself. So that's automatically
symmetric, all the symmetric polynomials.
Yes, all the symmetric polynomials in these roots give you sort of algebraic relations. If you take the, so for example, the last one, alpha naught, this a naught, is the product of these roots, alpha 1, alpha 2, alpha n, that's equal to a0. I don't know, plus minus, just check. But that's also an algebraic relation, and that's also automatically preserved by any permutation of the roots. But these are the obvious sort of algebraic relations. But there are less obvious algebraic relations among the roots, and those will depend upon the polynomial. These are true for any polynomial. But the subtle algebraic relations between the roots of a polynomial will depend upon that polynomial. Okay. So, for example, if you had this polynomial, here, I mean, all the roots are just powers of any one of them.
Yes.
You name any one of them, and the others are powers of that one. That doesn't happen for other polynomials. Okay, it happens for this cyclotomic polynomial. Doesn't happen for others.
That's why it's solvable.
That's why it's solvable. Its Galois group is actually commutative.
Just the z and p minus 1.
Yes, it's of z mod p minus 1. I mean, it's cyclic of order p minus 1. That's right. So,
I just
yes, sir.
So when you begin with the, we don't even know what are the roots. So how do we know what are the algebraic functions?
So that's a difficult meaning. It will depend upon the polynomial, but I mean, there's no general answer to the question. There's no answer to it. Meaning, some polynomials will have, depends upon the polynomial. For example, this polynomial, I was able to write these algebraic relations. So once you have a polynomial, what Galois said, he didn't say what algebraic relations will hold between the roots of some given polynomial. That will depend on the polynomial. But he said, whatever algebraic relations there may be, they have to be preserved by elements of the Galois group. So there's no general answer to that question. That will depend upon the polynomial. What
There is like a scheme. He's just saying it has to preserve, but it's not explicitly specifying. And we are figuring it out through this calculation. That's what.
So that calculation works for that polynomial. So each specific polynomial, you have to figure out what the algebraic relations between its roots are. Okay, so
But what you said earlier was that the Galois group is a substitute for knowing that, because the Galois group captures the information of what kind of relations there are.
that's right.
And that there is an algorithm to compute that.
That's right.
Even if you can't compute the algebraic relations directly. And so knowing the polynomial,
Knowing the
the
polynomial,
Galois group is the proxy for the
it is sort of a proxy for the algebraic relations between the roots of that polynomial. Yes.
Is it other way around? I mean, that if I know the Galois group of the polynomial, can I say what the relations should be, algebraic relations should be?
No, I don't know what to say, because many different polynomials can have the same Galois group. That's, for example, let's look at the simplest case. Let's look at an equation squared minus a equals 0. Then there are just two roots, root a and minus root a. And the only relation is that one of them is the negative of the other. But the arithmetic nature of this, so the Galois group is going to be just this group. It just takes one to the other. If it takes this to that, and anyway, so that's only possible. There are no more possibilities. So that's the Galois group, but you see, this can be the Galois group of many different equations. And not
That
just
is true,
Yes.
but it tells you therefore that all the roots must obey this relation. It should be a.
yeah, but I think this is too simplistic.
No, maybe not, because you could have a general quadratic equation where the roots are not negative
That's
of
right,
each other,
that's right.
but its Galois group will also be the same.
That is true. So you'll have, so if I take, for example, the equation x squared plus x plus 1 equal to 0, this is irreducible, and its roots are, let's say j. If j is one of them, the other one is j squared, and j squared is not equal to minus j. So here is a quadratic equation whose roots are not, if you call one of them j, then the other one is minus j. No, the other one is j squared.
No, but doesn't that depend upon what we mean by algebraic relation? Because if I define the root, sum of the roots is a constant, then all of these will be satisfied. So in this case, for example, j square plus j is equal to minus 1 will be satisfied. In that case, the root a minus root a adds up to 0 will be satisfied. So what does it mean to say it's an algebraic range? Is the question.
What does it mean to say, that can be precise. So, if you can find a polynomial in several variables, into which when you plug in those roots, you get 0. So, if some such definition can be made. But one doesn't think in terms of these things these days. No one thinks in, you are a physicist, maybe. So, let me give you a physics definition of the Galois group, because physicists like symmetries, right? So, here are the symmetries. Here are the symmetries. So, you can forget about everything that I've said till now, and you can start afresh. So, you take a field and take a finite extension. To such a thing, you can attach the group of all k automorphisms of L. So a field, I mean, you think of symmetries of geometrical figures, right? Of triangles or, but this is an algebraic object, and one can talk of the symmetries of this object as well. So these are what? These are sort of maps from L to itself, which preserve addition and multiplication. A field is something in which addition and multiplication are defined. And so a symmetry of L would be a map from L to itself, which preserves addition and multiplication. And it's a K symmetry if elements of K are taken to themselves. So the simplest example of such a thing is this. So if you take the complex number and set it to Z bar, that's a symmetry. And it takes, if your complex number happens to be real, then X bar is going to be equal to X. And this mapping, of course, preserves addition and multiplication. So if you have Z1 plus Z2, and if you take the bar of that, what you will get is Z1 bar plus Z2 bar. And the same for the product of two things. So that's a symmetry. Now, so this is a group. Okay. So let me call it G, and I can then talk about the points fixed by G. So these are all elements of your L such that sigma x is equal to x for all sigma h. So if you are thinking of, let's say, geometrical figures, you have this equilateral triangle, and one of the symmetries of this triangle is this reflection on this. And it's this point which is fixed. These 2 points are not being fixed. Similarly, in this algebraic object, some symmetries, there might be things which are fixed by every symmetry. For example, everything in K is going to be fixed by every symmetry, because that's how I'm just looking at symmetries which fix everything inside K. So, but the things which are fixed by every symmetry might be bigger than K. So K is contained in L, things which are fixed by this group. Okay. Whereas, if it so happens that if the things which are fixed by the group G is the group of all automorphisms of L, things which are fixed by G in L are a bigger, is an extension of K. If that extension happens to K itself, then you say that this L is a Galois extension. So take a finite extension of a field K, look at all K automorphisms of that extension, look at the fixed field, that is going to be an extension of K. It contains K because everything in K is preserved by every symmetry. By definition, we are only looking at those symmetries which leave every element of K fixed. So if, when you take the fixed field, it happens to be no bigger than K, then you call it a Galois extension. So that's how we think of it this way. I mean, what does it mean to preserve all algebraic relations? It just means that it's an automorphism of L as a field over K. It's a symmetry in that sense. Okay, so I don't have maybe
10 minutes?
10 minutes I can take?
Yeah.
Yeah, so I just wanted to quickly say something in the second memoir of Dalawat that's very important. It was sort of, it's not as well known as the first memoir. And the first memoir has become what is called Dalawat theory. The second memoir is here. So, he said, you take a field K, you take an extension L of K. He said, if it's of prime degree, then there are no intermediate extensions. Because what happens is, if you have an intermediate extension, E, then the degree of this times the degree of this is equal to the whole degree. Okay? So, if your total degree is a prime number, then there can't be any intermediate extensions. Okay, so let me give you an example. If I take 2q and if I join a cube root of 2, that's an extension of degree 3, so there are no intermediate extensions. But if I adjoin a fourth root of 2, then there is an intermediate extension because I can adjoin first a cube, square root of 2, and then a square root of that square root of 2. And so this extension is, it has an intermediate extension. Okay? So Dalawat said, L over K is primitive. That's the definition. If there are no intermediate extensions. Okay? So example, if K, this is the notation for the degree or the dimension of L as a vector space 1. Okay. So if the degree happens to be a prime, then L over K. So in his first memoir, Galois talked about extensions of prime degree. In the second memoir, he is generalizing that notion of prime degree, he is replacing it by a primitive extension. Extensions of prime degree are automatically primitive, and primitive is by definition something which doesn't have any intermediate extensions. Okay, so it's clear that this is a basic notion because every extension can be written as a succession of primitive extensions. That's very clear. Because either your extension is primitive, in which case there is nothing to do, or it is not primitive. Not primitive means there is some intermediate extension. I mean, that intermediate extension is either primitive or it's not primitive. If it's primitive, then you have got the remaining extension, you apply the same thing to the remaining extension. So basically it's clear that every finite extension is a succession of primitive extensions. This decomposition might not be unique, and in general it is not. But still, you have been able to write an arbitrary extension as a succession of primitive extensions. Therefore, yes.
Is it possible that there will be extensions which whose index is not prime, which are primitive?
Oh, yeah, that's a good question. Yes. So it is very much possible.
No, but why I'm asking is because it seems like L by K is primitive. So in that sense, L by K seems like a set of cosets of
No,
L by K. Because
Oh, wait a minute. There's no I. It's not. This is not a quotient.
then
It's L over K. I mean, that's notation. Huh? This notation looks like G modulo H. So that is a slightly slant thing, and this is a vertical thing. It just means that L is an extension of K. We are not looking at cosets or anything. No. But your question makes perfect sense. Your question was, okay, extensions of prime degree are primitive, but are there primitive extensions which are not of prime degree? And the answer is yes. There are many examples, and
So primitive extensions are always adjoining some root of a polynomial, or
that's any extension.
that's all, any extension?
Any
is
finite
okay.
extension
Okay.
is obtained by joining the
Obviously,
root of some
yeah.
polynomial,
Yeah.
but that extension may or may not be primitive.
Primitive.
So, for example, if it's of prime degree, then it's primitive, but there are extensions which are not of prime degree, but which are still primitive. Yeah. But here is a surprising result. Here is a surprising result. That's in the second memoir. If L is a primitive solvable extension of K, then the degree of L over K is if the N for some prime P, and of course some integer N. What Galois said was he proved that if you have a field K, he was not working with arbitrary fields. In fact, the notion of an abstract field came 100 years after Galois. So, if you are attributing, but what he did can today be translated in this language. He said, if you start with a field K, take a primitive extension of K, which happens to be solvable. And what does it mean for an extension to be solvable? That's what I was trying to explain here. So basically you have L over K, and then I said this corresponds to adjoining one root of some irreducible polynomial. This corresponds to adjoining all the roots of that polynomial. So, and this is called the Galois closure of L. Now we can talk of the Galois group of L hat over K, which is just another notation for the group of all order morphisms of L hat as a field, as an extension of K. So it's a group of all symmetries of L hat. Okay. So if here is the definition. If this group, if this L hat over K is solvable, then we say that L is a solvable extension. So that solvability of polynomials in terms of radicals, that has got transformed into this. That's what it boils down to. Polynomials have now been replaced by extensions. The solvability of a polynomial by radicals amounts to this. For a finite extension, you take its Galois closure, look at its Galois group. If that happens to be a solvable group, then you say that this extension is solvable.
L is some K alpha, right? For some alpha.
That's right.
So L it's for particular root. So but L hat is like we are trying to all.
Yes.
So is it saying that for all K alphas will be called
Yeah.
solvable?
Yeah. All K alphas, meaning K alpha 1 will be called solvable, K alpha 2 will be called solvable. Is that what your question is? Yeah. Because this is the same for K alpha and K beta. If alpha and beta are two roots of the same polynomial, then this is the same for them. And the definition of solvability depends only on this. Right. So, here is a surprising thing. The surprising thing is that you are just starting with some extension L over K. You aren't saying anything about its, you're not assuming anything about its degree. You're only assuming that, first of all, it's solvable in this sense, and secondly, that it's primitive in the sense that there are no intermediate extensions. And this theorem of Galois says that it forces the degree of this extension to be the power of a prime number. Okay, so that's what Galois theorem is. Okay, so now
L hat is also an extension over L, right?
it's an extension of L as well.
Yeah. So you could think of L as an intermediate extension between K and
Yes, so L hat is not going to be primitive.
Yeah, L hat won't be primitive, but L primitive
If there are no
L hat is
intermediate
solvable.
extensions here. Yeah, that's right.
And another question, sir.
Yes, yeah, please. I like questions.
Okay, so if f is one such polynomial whom you have, whose root you have attached,
Yes.
the Galois group of f, is it the same as this?
Yes.
It is exactly the same.
Yes. Absolutely.
I mean, that time when you're asking, like, you said that by attaching roots only we extend, but the definition of a finite extension over an underlying K can be defined independent of any polynomial. It's just an abstract thing also.
Yes.
So, how do you reconcile it?
So the reconciliation is that if you take an abstract extension, which happens to be of finite degree, you can always find a polynomial whose root, when you join, you get that extension. Other questions? Yes.
So for example, we take a polynomial, the sum over x to the power n, 0 to
Sorry, say it again.
sum of x to the power n, 0
Yes.
to 0 to n.
Okay.
And so that extension, that's a primitive extension, right? Because just one solution.
No, that's not even an irreducible polynomial sometimes, right? So you are saying, you look at the polynomial x to the n plus x to the n minus 1. So, first of all, we are looking at irreducible polynomials. So, without being irreducible, you don't get an extension like this. And primitivity is defined only for extensions, finite extensions. So, that amounts to saying that there are no intermediate extensions. So, that polynomial will not be irreducible. And actually, whether there are, we are defining a notion, but for a given field K, whether there are any primitive extensions or not, will depend upon K. So one of you asked whether, a primitive extension does it necessarily have prime degree? And I said, no. The degree can, doesn't have to be true. But the real answer is, okay, for some fields, it's true that every primitive extension is of prime. For example, if this is a finite field, then every primitive extension is of prime degree automatically. That's a property of finite fields. But what I meant to say was that there are fields which have primitive extensions which are not of prime degree. So what primitive extensions there are will depend on the field. Yes.
In non-solvable case, there's no such simple result of degree.
Maybe a historical question.
Yes.
Did Galois give any hint that he was, did he indicate that his ideas could be applied to differential equations? Or did differential Galois theory have was it in some footnote of his that you could apply the same sort of reasoning to differential equations?
Yeah. There's somebody called Yves Andre, and I'll sort of refer you to his papers. He might have something to say about this.
Because most of what I've heard is from like Burkhoff and these kind of people.
Burkhoff?
Much later that.
No. If you really want to know what Galois actually himself did, there's this excellent book. There's a fellow called Peter Neumann. So let me make a small digression to tell you about this person. He was a professional group theorist all his life. After he retired, he decided to become a historian of mathematics, and especially of what Galois did. He just brought out this excellent book called The Mathematical Writings of Galois, in which every little paper left behind by Galois has been analyzed, all different versions have been examined, and if you want to get an insight into the mind of Galois, this is the book that I would recommend. Came out about a couple of years ago when Galois' 200th anniversary was being celebrated. And the name of the book is, I think, The Mathematical Writings of Galois or something. Anyway, so.
And the book by Yves Andre, is it you're referring to the book on differential
Yves Andre
modules?
does have a book. He's a professional mathematician.
He
So
has
he's
a
not a
book.
historian, but he has an interest in differential equations and Galois theory applied to differential equations.
I think he has a book on differential fields or
Right.
something like that.
Yeah, so that's why
You're referring to that?
various writings.
I see.
I'm not talking of any specific writing, but I think various writings of Yves Andre would contain, and there are also some talks by him. If you understand French, then you can listen to some of them. So let me just finish by. I have very little time left for my footnotes. So that's section 3. So these are the footnotes which I happened to make in 2012 and 2016. So this was sort of for prime degree, and this is for primitive extensions. So what is the content of these things? So let me just explain it for these primitive extensions, because this theorem is here on the board. Galois says if a primitive extension is solvable, then its degree has to be the power of a prime. But this doesn't tell you what all primitive solvable extensions there are. It only tells you that the degree is going to be the power of a prime. Okay, I give you the power of a prime. Can you tell me? And I also give you the field. Because the answer will depend upon the field. What extensions there are depends upon the field. So we start with the field, We start with a prime power. We start with a field K and a prime power P to the n, and we ask what are the primitive solvable extensions of K of degree P to the n. That's a valid question. Answer will of course depend on the field. And this is what one can sort of now say. One can parameterize these things. The primitive solvable extensions of K of degree P to the n can be parameterized, can be given, one can give a bijection with a known set. So it's not very complicated to describe what this other set is, but it's something which can be worked out. If you know your field sufficiently well, then you can work out this right hand side. And your left hand side, which is the set of primitive solvable extensions of K of degree to the n, is in bijection. This thing. So that's what these footnotes are.
This object which is bijective, is it a geometric object? Or?
No, it's something like this.
It's like a moduli space of primitive extension.
See, moduli spaces usually are there when you have some sort of continuity.
Yeah.
Here everything is discrete.
Okay.
So it's just a set of some pairs. Okay, so you have your field K and you have a prime P and an integer. So given these three things, you look at an algebraic closure of K, and you have what is called the absolute Galois group. Then you will have to take degree n representations of this Galois group with coefficients in Fp, the finite field of Fp. So that's one of the ingredients, and then there are other things which are not very difficult to describe, but I don't have time.
But you have to classify all representations of the Galois group.
You are absolutely right. So in general, you can't do it. So that classification will depend upon your field.
Right.
I was particularly interested in these things called local fields, which are central in number theory. And for those fields, you can classify these representations. And that was actually the beginning, the origin of the problem for me. I was interested in these local fields, and I wanted to classify primitive extensions of these local fields. It so happens that for these local fields, every extension is automatically solvable. That's another wonderful thing which happens for these local fields. And so, starting from those local fields, I was led to consider the general question of classifying primitive solvable extensions. I came across this theorem of Galois, which said that the degree has to be the power of a prime, but doesn't tell you what all extensions there are. Suppose the degree is given to you, the field is given to you, the degree is given to you, what are the extensions of that degree which are primitive and solvable? And I'm not writing down the statement, but you can now write down all these extensions. So it involves classifying, you are right, the representations of this absolute Galois group over finite fields and yes.
Sir, in that second member when you started there, you talked about the splitting field, right?
Right.
You took the separate polynomial, you are enjoying the roots to like k, and you are talking about the splitting field, and that's how you talked about the Galois group.
Yes.
But in that first memoir,
yes,
you then talked about the general nth degree equation, like x to the power n and all that. So if you are considering there that it has n roots, then you have to take C is algebraically closed, right? So we are basically considering the splitting field over there also. So how can we talk about these things there? I mean, the proving that C is algebraically closed or that polynomial has n roots, the irreducible polynomial, without talking about separability and area. This the extension k alpha over k, without talking about that, how do we show that it's algebraically closed over there?
Let's see the field. So the question is,
in the first memoir,
yes,
without talking, in the first memoir, how to show that equation, that nth degree polynomial equation
has n roots.
Yes.
Yes. So
It was oil Galois before Gauss or around Gauss?
is after Gauss. So Gauss is 1777 to 1855, and Galois is from 1811 or 12 to 1831 or 22. These are the dates. Yeah, so in some, you see, maybe you asked it because Gauss proved that C is algebraically closed.
Using algebra?
Not using algebra, whatever, I mean, you use mathematics. So, but this is kind of known already that an equation of the n has n roots. Before Galois, that was known.
Any other questions?
There's also a proof by Euler and Lagrange, right? With the clever induction on 2 power n fundamental number.
I don't know whether this goes back to Euler. No, I don't think so. I know that Euler didn't prove that C is algebraically closed. This is around Gauss. And the other names which are sometimes mentioned are D'Alembert, but not Euler. Euler was before D'Alembert.
I read somewhere that Euler proved and Lagrange fixed it. But it's not a complete proof in the modern sense. I don't know exactly.
So there's a proof. I think what you are talking about is there in Lang's book on algebra. There's a proof in the exercises involving extensions of degree a power of 2 and so on. So yeah, that's the closest using Galois theory. Nowadays it can be seen as using Galois theory, but even that I don't think Euler would have known it. I'd be surprised. Yes.
When you solve an equation x cube minus 2 equals to 0.
Yeah.
So if you get the Galois extension by the q of q root of 2 and q root of 1. So why did you consider this thing q root of 1? Why was that necessary?
Oh, that's because so I just write j for this very smaller thing. So the 3 roots of x cube minus 2 are, so alpha, which is a cube root of 2, the 3 roots are alpha, j times alpha, and j squared times alpha. So in order to get these 3 things, I need to adjoin not just this, but also this, because these things are.
Thanks a lot.
Okay.
It was wonderful. Thank you.
I hope it was accessible to the
Everyone, I
listeners.
think so.